Hello, welcome to Chapter 7 of Math 100. We'll be discussing geometry, as you can see. Ooh, geometry. Geometry, of course, is the math of shapes, essentially, right? We all took geometry class in high school, I'm pretty sure. This will be a refresher. I'm not going to dive too deep into the geometry. It can get wicked crazy, right? But we're going to avoid the in-depth analysis and instead stick to the basic stuff you're probably going to run into your day-to-day life and the basic building blocks for whatever math classes you take after this. We'll start with angles. So, as said previously, geometry is the branch of mathematics that deals with portions of relations between figures in shape in space, i.e., shapes. Geometry is the math of shapes. All these are shapes. All these are very different shapes. We have a circle here. From circle, we can get a radius, we can get a diameter, we can get a circumference, right? Triangles, especially right triangles, whole ton of math in there. SOHCAHTOA, three-dimensional shapes, very much a volume calculation, right? Just two lines can form a vector and an angle and have a distance and displacement, everything like that. But as most basic principle, a one-dimensional shape, a line, counts. Lines are shapes. Lines have rules that geometry talks about. A line extends indefinitely by definition, but a portion of a line called line segment has a beginning and the end. Usually, when we talk in math class, we usually talk about line segments or point A to point B, right? We've probably heard those phrases before. The distance between point A and point B is blank, what have you. Technically, we call those line segments. And notation the book says here, lines have arrows, line segments have dots. More or less, that's what you see throughout all your textbooks and day to day. If you have a line that starts in a certain location and then goes on continuously, we call that a ray. These examples are of lines that are straight. Lines can bend, lines can wiggle. Lines are going to do what lines want to do at the end of the day. But yeah, line segment, line, ray. Describe the same shape, but in different sizes, essentially. An angle is made up of two rays that start at a common endpoint. We call the endpoint the vertex, and we call the individual rays sides. Angle is an angle. You probably all used protractor before, right? Or something along those lines, a spirit level, something like that. But when we get into angles, now we start talking about the math behind it, because lines, rays, line segments, these all, in general, when you run into these in the real world, these are more so utility. The graph you're looking at has line segments on it, sort of a conversation. The math behind lines is calculus, really, because how a line changes is a calculus conversation, and we're not at that point yet. So instead of using lines and rays as the math themselves, we use them to build angles. And then, of course, if you close this off of a triangle, right, we'll get to that. But important terminology here is vertex, side, and angle itself, right? The two rays are called the sides of an angle. Yeah, that's a good way of putting it. And the point which to me is called the vertex of the angle. The difference between the two sides, we measure that in what's called degrees. This is again something we've probably seen before. We all know what 90 degrees looks like, right? That's perpendicular. 45 is halfway between 90, 180 is all the way over, etc., etc., etc. We've experienced these in the real world setting. Yeah, not too much at this point to talk about, right? But it's good to get these information down. And the sign for degrees is the same sign that we use for temperature, degrees. I don't think they're related to each other. But yeah. amount of opening of an angle. Sure. Most common degrees, as I said already, are 45, 90, 180, 360. This has to do with definitions of pi and things like that. If you're interested in math and math theory and math history, if you prefer, figuring out why 360 degrees is a complete circle is a fun story. I suggest you look it up in your spare time. Random documentary on YouTube where you're doing something more important sort of time. It's pretty interesting stuff. But yeah, it is important to realize these conversations. If you do a 180, you're in the opposite direction. If you do a 360, you're back to where you started from. And 90, of course, is said to be perpendicular. And then all these have spaces between them. 45 would be between 0 and 90, right? And that's at 135, I think, is between 90 and 180. And then 270 is, I think, 270 is straight down here, etc., etc., etc. The more you use these things, the more natural they become. There are numbers that you've heard of, though. Two lines are perpendicular when they meet a 90-degree angle. That's the definition of perpendicular. You guys have all heard of right triangles. We talked about right triangles at the very beginning. The right triangle is defined by two sides being at 90 degrees to each other. We show 90 degrees with a square here. That's the universal way of saying these two sides are 90 degrees away from each other. And this over here is actually kind of important. This is a very common way of writing angle. What this is saying is the angle of the sides A, B, and C, where in this example, B is the vertex, right? And A and C are the sides. The vertex is the middle letter, as it says, right? And this square, again, represents 90. If that square is not there, you do not have a 90-degree angle, unless you're told that you have a right triangle, right? Acute and obtuse angles. An angle that measures 180 degrees is what we call a straight line. Again, what is a 180-degree turn? That's facing the opposite direction. You rotate half of a circle to get there. Therefore, you have essentially turned around in space, right? An angle whose measure is between 0 and 90, we call an acute angle. So this is basically a full turn. If you go any further than that, technically you could have just rotated the other way and got there faster. So we only care about 180 degrees usually because that's the most you can turn without an easier way of doing it. If you have an angle that's less than 90, we call those acute angles. And that simply means it's a small angle, I don't know necessarily if there's a reason why it's acute. I like to think it's because small things are cute, but I don't know the exact etymology and history of that word. You probably are aware an angle greater than 90 is what we call obtuse. Or technically between 90 and 180, 165-degree angle down here, that is an obtuse angle. A 50-degree angle here is an acute angle. Again, a common question is, what if we go over 180? What's a 190-degree angle? Well, and I think we can get this in a bit, but if you say you did a angle like this, that technically, right, would be way over. But then we get into a left-right conversation. Couldn't I just go this way and get there faster? Yes. So this is an obtuse angle because it's greater than that 90-degree spot. And this right here would be a acute angle because, right, we probably would read it just go in the opposite direction. But I think I'm stepping myself ahead a bit there. All right, back to it. So actually, let me move this. You guys can't see that, but it's in my way. There we go. Other terminology that is important. What is a complementary angle? A complementary angle is an angle whose sums measure 90 degrees. Adding angles, adding degrees is just adding, except that instead of 90 being a number, 90 is a defined proportion, a defined object. 90 degrees is perpendicular, as opposed to just being a number. So if you go 59 degrees and then you go 31 degrees, you have in total traveled 90 degrees. And of course, 31 plus 59 by itself is 90, right? 31 plus 59 equals 90. Therefore, 31 degrees plus 59 degrees, again, equals 90. If the angles instead add up to 180, we call those supplementary. Right, 55, 125, same concept. It doesn't really matter the size of the angles. That what matters is the end result being 90 or 180. That's where you get complementary versus supplementary angles. You're probably mostly going to see complementary angles in your day-to-day. I don't see supplementary very much, but I don't know what you do for a living. So, reminder, if anyone has any questions, you can put them in the chat, raise your hand, barge into the conversation, do whatever you need to do. So, questions involving angles. Angle B measures 47 degrees. So before we go any further, you can ask yourself, all right, is that an acute angle and obtuse angle? What does it look like? Well, 47 is less than 90, right? Is less than 90 degrees. So that makes it acute. It's not part of the conversation, but it's good to have this foundational stuff set out. It's acute. What does it kind of look like? Well, I know 45 is basically like that. 47 is pretty close to 45, so that's probably about 47. Is it exactly 47? I don't know, right? But it's kind of close enough. Good things to have usefulness in the back of your mind, right? Now let's go on to our questions here. Find the complement of the angle B. What is complement? Well, complementary angles sum to 90, so a complement probably has to do with complementary, meaning these angles should, angle B and its complement should sum to 90 degrees. Supplement, well, that looks a lot like supplementary, so supplementary angles should sum to 180 degrees. At this point, we can probably all do that math. 90 plus 47 plus what equals 90, or 90 minus 47 equals, because addition, subtraction are opposites. Get ourselves the answer we're looking for. Fantastic. Easy math, right? We've established the basics of mathematics in the first couple of chapters. Now we're just applying them in different ways. We apply them with fractions, we apply them with decimals, now applying them with angles. But the math still stands. It's just, I'm throwing in lots of weird words like complementary and supplementary and, all this other crap. Vertical angles are angles that are opposite each other, but always have the same measure. Now we're starting to get more into polygonal math and stuff like that, right? But a vertical angle would be X and Z, because these two angles are opposite of each other. They're verticals of each other. Y and W are the same way. They're verticals of each other. They are the same angle, but opposite directions, if you will, right? If you remember to your coordinate systems, right? This would be 1, this would be 3, right? What quadrants? Yeah, quadrants. There we go. The quadrants of your Cartesian coordinate system. Kind of, if you need the parallel, that would work for you. Two angles that share a common side are called adjacent angles. Y and X are adjacent because they share a common side. This side. And then X and W are adjacent because they share this side. W and Z are adjacent because they share this side. And then finally, Y and Z are adjacent because they share that side. Right? Pretty straightforward. Again, these are more definitions than they are unique math. But I can ask you what are the adjacent angles, and you can point them out to me. Right? Other important, now this is fun concepts. Other important ideas include parallel lines. The definition of parallel means they don't touch. Notice these are lines, they have the arrows, they technically go on forever and ever and ever and ever and ever in all different directions. But no matter how far these travel, they're never going to touch each other. They're never going to come in contact with each other. We define that, we draw that as these two lines between them. That means they're parallel. They're never going to touch. We do have things that are parallel. We think things can be parallel, although gravity concepts are hampering that. But in math, we don't care about that usually, right? Line P shown here is a transversal that intersects lines M and N, right? We're dropping a lot of jargon, a lot of terminology here. Line has a very specific definition. Line means goes on forever, right? P represents the way to signify it. Transversal intersects. What do those things mean? Well, a line that intersects two or more lines at different points is called a transversal. P crosses N here and crosses M there, not at the same point. Therefore, it's transversal. Intersects means crosses, means touches, if you will. Line M and N don't touch each other, but line M and N do not touch each other, but P touches both of them there and there. If these had numbers on them to signify distance, right, these would be crossing at different distances. Then you could expand this out later on in classes, talk about calculating speeds and what have you, but we're not there yet. Cool. Again, I'm just throwing out a bunch of terminology at you. If you got any questions, when we go back, explain something more, let me know. Comment in the comments below if you feel that's necessary. I can definitely go into that, or some of the classmates can go into that, right? Anyways, let's get into this. Alternate interior angle. Alternate interior angles. There we go. These are two angles that are on opposite sides of a transversal and between two other lines. What? What does that mean, right? That's a lot of stuff going on there. Well, let's break it down. Two angles, right? We know what an angle is. That is two rays form an angle. Good. That on opposite sides. What's opposite? Well, opposite would be, if we go back to the example here, X, Y, Z. X and Z are opposites. Of the transversal, what does transversal mean? Well, transversal is you have two parallel lines. Transversal was the one that intersected them. So, alternate interior angles are two angles that are on opposite sides of the transversal between two other lines. Here's a transversal between two other lines. The alternate interior angles must be the opposite angles. There we go. Give it a spotlight back. Two lines transverse. They intersect. They cross at separate locations, right? They have opposite interior angles between them. Hey, look at that. That is a lot of words to kind of describe something that you could have known by just looking at the alternate interior angles. A and B are look interior, right? They look inside something, and they alternate, meaning they are flipped from each other. A and B are flipped. And they're all angles, as said previously. Right? We'll kind of get into math to where you can get lost in definitions, or you can stop, sit, wait a minute, and say alternate interior angles. What do I think that would be? Well, that'd be things on the inside that are alternate of each other and their angles. Voila! Yay! Go team. I guess I'll leave this to you. If I said C, D, would those be alternate interior angles? And then what if I said E, F? Would those be alternate interior angles? Or E and F? of C and D? Stop and think about the definition. Think about both the technical definition and just what that means. Corresponding angles are two angles that are on the same side of the transversal and are both above or below the other two lines. Whew. Again, lots of stuff going on here, right? We have two angles that are on the same side of a transversal and are both above or below other two lines. A lot of stuff going on there. But we can break it down. We can stop and think what we're talking about here. And maybe we can picture in our minds what's going on before it has to be drawn out to us, right? Take a few moments, pause the video if you're watching YouTube. Take a few moments. Think about the previous example. Think about the previous example. And say to yourself, all right, what do corresponding angles look like? In this case, they want you to use C and D. Spoiler warning, right? Is that kind of what you were picturing? You have two angles, C and D, two angles. They're on the same side of the transversal. This is the transversal here. The P is the transversal. M and N are parallel. P is transversal. Intersects at two different locations. Same side, meaning left, right, up and down, if you will. And are both above or below the other two lines. In this case, M and N being parallel. C is below M, D is below N, and they're both on the same side of the transversal P. Cool, right? Usefulness to all this depends on what you do with your day-to-day life. Finding corresponding angles can be super useful for, I imagine, civil engineering construction purposes, making sure that this is a good way to make sure that P is at the angle you need it at, because if C and D are different, then P might be curving in some way, right? You don't want that. If you want P to be straight, C and D need to be equal. And that's the math. I mean, building a deck uses these basic principles. Just we don't say corresponding angles usually. You just say, hey, are those two correct? Parallel lines cut by a transversal. If two parallel, okay, let's start highlighting some stuff here. If two parallel lines, we know what parallel means, right, are cut by a transversal, or intersected by a transversal, then the measures of the corresponding angles, what we're looking for here, are equal, and the measures of the alternate interior angles are also equal. Cool. Definitions here. We know, there we go. We know what alternate interior angles are. We just covered it, right? So we know what the alternate interior angle is. Now we're referring to, there we go. Now we're referring to corresponding angles with parallel lines that are cut by transversals. So, again, stop for a second. Try to picture what's going on here. Pause the YouTube video if you need. Try to picture what's going on here before you get there. Can you take all these big mathy-looking words and have it make sense to you, given what we've talked about before? You probably can, right? Because these are all jargon-esque ways of saying things that, in all honesty, we do rather regularly. We do this. If C is 50 degrees, by definition, D is 50 degrees. And by definition, B is 50 degrees. B, C, and D all are the same angle. If you measure D and you measure B, you know that C is correct by definition. Why? Again, because of the way that lines work. And if B, C, and D are all the same, that means M and N are parallel. Right? A lot of information coming out of this stuff. Angles are super useful, right? Not just in getting a decent grade on chapter 7, but in your day-to-day lives. That was lines. Let's cover rectangles and squares. How do we define stuff, right? What is the perimeter of a rectangle? In a rectangle, any two adjoining sides means together sides are perpendicular and the lengths of the opposite sides are equal. A rectangle, by definition, has these two sides. Let me draw it here. This and this are equal, and then circle them. This and this are equal. That's the definition of a rectangle. The perimeter is found by adding all sides together. If you have a square, meaning all sides are equal, then instead of adding all the sides together, you can just, I guess you could just, it's not necessarily exclusive to squares, but you can find perimeters or how far it is to walk the length of it by doing 2 times the length plus 2 times the width. Again, this works for rectangles and squares that follow the definitions. If the opposite sides are not equal, you don't have a rectangle, things get a bit more complicated. So lengths on all sides, shown here, shown here. Cool. Feel free if you need to go back to the slideshow or you're in your homework to look up these equations if you forget them, or just Google them. Right? Not everyone has all the geometry equations memorized. There's nothing wrong with looking it up. Question. Find the perimeter of a field that is 6 miles long and 3.5 miles wide. Well, the question was kind enough to give us an L and a W. We talked about this. We talked about variables a while ago. Sometimes variables indicate exactly what they are. Instead of doing X and Y or N or something like that, we do L for long and W for wide. Right? So we know what goes where, and then we'll add a simple equation where we plug in the numbers and solve it. Of course, we solve it using PEMDAS. Please excuse me, dear and static, parentheses, exponents, multiplication, division, addition, subtraction. So we know that 2 times 6 happens before 6 plus 2. Otherwise, you get the incorrect answer. Find a perimeter of this field being 19, what? 19 miles, right? It's not shown here, but this 6 is miles. We talked about units last chapter. 3.5 is miles. So these both would be miles, and this is miles. Important distinction to put the miles in there, especially if we talk about units in the question, we need units in the answer. Hey, look at that. Woohoo! Go team. The perimeter of a square is 4 times the length of its side. Why? Because all the sides are the same length, right? If every side is 3.25, instead of adding 3.25 plus 3.25 plus 3.25 plus 3.25, we could just do 3.25 times 4 and get the same answer. Cool. Find the perimeter of this shape. Now we want to do an issue where we don't necessarily have dedicated lengths and widths, do we? Right? We have all this weirdness going on, all these numbers that kind of don't exist. What are we supposed to do? Well, you add up all the sides, right? And this is actually kind of a tricky information because notice there's 2 sides that we don't know, right? It doesn't tell us this, and it doesn't tell us this. But are those 2 important to know? Could you figure them out? The answer to both those questions is, well, are they important to know? They're not. Can you figure them out if you need to? Yes, you can. I'm going to let you ponder that for a little bit. Again, pause the video if you're watching on YouTube and just think, why don't I need to know X and Y to solve the perimeter? Or if you're sitting here in the Zoom lecture, think about it for a little bit. Maybe, how about this? If you're sitting in the Zoom lecture, I'll give you some extra credit on this assignment if you type me up a nice paragraph explaining why X and Y aren't needed to solve it, and you solve for X and Y. I'll give you some extra credit, all right? It's extra credit you don't need to do if you don't want to, but it can be done. Especially since you know the length of the perimeter. Area of a rectangle. What is area? Area is a two-dimensional shape. Now we're getting dimensions here, right? Technically, perimeter is 1D. This is 2D. Notice here, the length and width are not added. They're multiplied by each other, right? So you have a field that's 6 miles long and 3.5 miles wide. Well, the area is 6 times 2.5 or 21. Notice here that we are squaring the miles. Square miles, so we put a little 2 up here in front of the unit. Because this 6 and this 3.5, oops, and this, oh, come here, eraser, there we go. And this 3.5 both have units of miles. So this is going to have a unit of miles times miles. And what's a shorthand way of saying something times itself? Well, 2 times 2 is the same thing as 2 squared. So miles times miles is miles squared. Area has units squared. Yep. Again, same process. For a square, it's even easier. Look at the side. Well, the side's 3.25. I'm just going to square that. Get my area of this square as 10.5625 inches. Real simple math, right? When we break it down into these weird looking shapes, like this shape here, this one isn't quite as easy to take area of because I don't have a defined length and width. So what we do for this question is we chop it up into questions I can answer. In this example, regular old rectangles and squares. Chop it up into questions I can answer and then add those total. Because the total area is going to equal the area of all the parts added together. Right? If you want to know the square footage of your house, you don't measure your house necessarily. You measure you take all the sizes of the rooms and you add them together. That gives you the square footage of your house. Because your house may have all these weird shapes and divots to it, and it may not be a perfect rectangle or a perfect square. Usually it's not, right? If your house is a perfect rectangle, hey, congratulations, you live in a very geometrically satisfying house. But if that's not the case, we can stop and think about what we're doing, formulate an attack plan, and find areas of, for example, squares, rectangles. I would argue rather simply. Again, this math is all math you've done plenty of times. This math you've done plenty of times. It's applying it that can be the tricky part. Parallelograms, trapezoids, and rhombuses. Oh boy, lots of big, fun, scary-looking words, right? No, not really. Not difficult stuff to go over. A quadrilateral is a four-sided figure. Technically, rectangles and squares are quadrilaterals. A rectangle is a quadrilateral that follows certain rules. A square is a quadrilateral that follows, again, certain rules. Likewise, parallelograms and rhombuses are rectangles and squares that only follow part of those rules, right? Because a square is all the lengths and all the angles need to be the same. A rhombus is if your angles aren't all the same. These angles here are different, right? This one is acute. This one is obtuse. Different angles, but same sides, you have a rhombus. Again, same concept of the parallelogram and the rectangle. Cool. I'm glad we did that graphic. The perimeter of a parallelogram is the distance around the parallelogram, and it's true for the rhombus. Kind of the exact same thing, right? Because the thing we changed was the angles, not the sides. So the rules stay the same. The area of a parallelogram is found by multiplying its base times its height. Different from a rectangle and square, although is it? Right? Any side of the parallelogram can be considered the base, and the height is the shortest distance between the base and the side opposite of the base. So perpendicular, base side are perpendicular to each other, right? This may look different from what we were doing before, but if you stop and think about it, this isn't any different from L times W, right? There's no difference here. Just we can't really call length and width because we have all these weird angles going on. And then, of course, I'm going to skip forward a little bit here. If you're good with your triangle math, you can see what's going on with the area of a triangle and what we're doing here. Because notice, right, this triangle here and this triangle here look pretty similar, don't they? They're just opposite versions of each other. Again, so when we get to area of a triangle, think back to these examples, you're going to see what we're doing here. It's kind of fun. The area of this parallelogram is its base times its height. That equation looks awfully similar to what we did previous. Area of this rhombus, same idea. Right? Again, when we're going over these questions, feel free to look up this slideshow. It's on Moodle. Google the equations if you want. I'm not having you memorize these things. Trapezoid is a four-sided figure with two parallel sides. At this point, we are escaping the congruency of angles. Notice this guy has no angles that are the same. This guy only has two. This guy has two sets of angles that are the same. This has two angles that are the same. This has no angles the same. All considered trapezoid. This is not the only trapezoid. Trapezoid is defined by parallel sides exclusively. And the perimeter is, well, the perimeter. That's no different. I'm not going to belabor this point. Height changes a bit. Again, because you can't trust angles to be similar. So we do have a more complicated definition of height. But again, I'm going to stress this. This is not difficult math to overcome. The thing is, you just need to remember your order of operations. And you need to find out what goes where. When you're given a question on this, such as this guy here, my suggestion to you is, first of all, to write out the equation. You look at this. If you know the equation, actually write the equation with the variables. Then fill in the variables. Then write your knowns before you fill in your variables. Meaning, okay, I'm solving for A, so I need HB, little b, and big B. So what is H? H is the height, 5.5. B is the base, which is what we're going to call 6 here. Capital B is the large line, which we're going to call A here. And, right, might as well point this out. Does it matter which B is which? No, because they're both in parentheses, right? Yep. This base and this base, if I get them backwards, the math doesn't care. But I can't get H messed up with a B because I'm going to have bad times. Good. If you have any questions, this is pretty straightforward. But if you have any questions, leave them in the chat, raise your hand, blurt it out, whatever you need me to do. Or if you want, you can wait till the end of the recording to ask questions. It's up to you. I'm fair in that way. So we did 1D shapes, lines. Then we jumped up to 4-sided shapes, quadrilaterals. Now let's step back to 3-sided shapes, triangles. Triangle, triangle, 3 angles. Whoa, who'd have thought that name, right? These are 3 different very common shapes of triangles. Remember what they're called? Ooh, right? Notice this one has a square in the corner of it. What does that mean? We talked about this already. Important definition of a triangle. Well, that's common, easily forgotten. The 3-side, 3-angle thing, sure. But the sum of the measures of all the angles in a triangle equal 180 degrees. If you don't have that, you don't have a triangle. What happens if you break that rule? Well, your triangle technically doesn't close on itself. Right? If this angle over here was 17 degrees, that would open this up and it would look like that. You would have a disconnect here. Therefore, you would have a closed shape. You would have a knot. Finding measurements of angles, follow the 180-degree rule. Write out your equation, solve what you need to do. Add these guys up, subtract it over, right? Again, the application is new, but the math is old. You know how to add and subtract numbers. You just need to realize how to write the equation. Take your time, write your equations out, use your work, use your paper. Don't just skip stuff because your words are going on paper. Shoot me a message. I will bring you a ream of paper if you're running low on paper. That's not a good excuse. I'll go ahead and plant a tree outside my house for a ream of paper I give you, if that's really a concern. Perimeter follows the same rules as quadrilaterals. Add them up. Cool, not too bad. Said here, two types of triangles. Remember I said at the beginning, what are these triangles we're talking about here? Isosceles equilateral triangles would be examples of two common special triangles. Isosceles we define as a triangle with, by definition, two equal sides to it. In this case, these left and right sides are equal to 12, and this base side is 5. Isosceles. Equilateral triangle is, well, everything is equal. A scalene triangle, that's the one where nothing's equal, and of course, everyone's favorite, the right triangle, which has a little square in the corner. Isosceles, equilateral, scalene, right triangle. Everyone forgets scalene. I don't blame you. It's like every other triangle that exists is a scalene, so it's kind of hard to remember that. But it has a name. Area. Right? I hinted to this before when we were talking about the trapezoids, but triangle area has a specific equation to it. The height of a triangle is the distance of a line drawn from a vertex perpendicular to the opposite side or to an extension of the opposite side. Wow, that's a lot of words. Right, again, break it down, figure out what we're talking about here. Height of a triangle is the distance of a line drawn from a vertex perpendicular to the opposite side or to the extension of the opposite side. Those are our key words there, right? Height equals blah, 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 blah. If we look at a triangle, maybe this will make a bit more sense. The height is the tall part of the triangle. The base would be what the triangle is sitting on. Cool. So the height of the triangle is the distance of a line drawn from a vertex. In this case, the vertex is right here, or right here, to the opposite side. The vertex, the base, the opposite side is up here. The opposite side is up here. Or in this case, we're going to have to extrapolate, which is the point of the or. And that gives us how tall the triangle is. Once we know how tall the triangle is, we can use that information to find the area based on the equation. Area equals base times height divided by 2. The area of the triangle is the base times height, right, divided by 2. Once you know the height on the right triangle, it's easy. It's just a side. For other triangles, you're going to do a bit more calculation. But once you know the side, once you know the height of it, you calculate area. And again, throw back to that picture of the trapezoid. You see the interesting stuff that goes on. Where was I at? This guy's, right? Look at these triangles. What are we noticing here, right? Because this was just base times height. It's two triangles. And a triangle's area is base times height divided by 2. The rhombus is two triangles stuck together. Area is base times height. Focus on triangles, though. Sorry. The other cool thing that I want you to notice here, and this is a clue to importance here, notice the right triangle has that square built into it automatically, but the heights are determined based off of these squares. Essentially, we are creating a bunch of right triangles here, right? This right triangle here, this is a right triangle here. Except once we know the height based on that right triangle, our base is going to be different depending on equilateral or scalene triangle. Little teeny base here, smaller area. Big wide base here, bigger area than right triangle. But at the end of the day, the math is easy. Keep stressing that because it's important. The math is easy. We're not going to get into super complicated geometry, triangle math here, but you can calculate this stuff. And also, you're going to be given questions of find the height given area. If I tell you A, can you figure out H? Make sure you can. That's going to be an important one. We can use all the rules that we've talked about so far, smush them together if need be to solve problems. What is the area of this figure here? Well, that's a rectangle plus a triangle, a scalene triangle by the looks of it. Area of a rectangle is length times width. Give us this. Should be in yards. There we go. And then the triangle is defined by BH divided by 2, base times height divided by 2. It's not labeled, but it's important to know that since this is a rectangle here, if this is 129, that means this is 129, right? By definition of rectangle. I don't tell you this guy is 129 yards, but you know that's true because it's a rectangle that we're looking at. So I can draw my answer out, get my yardage, and then my area would be, actually, no, these are yards squared, ain't they? Ooh, someone should have called me on that. And then to find the total area between the two, I add them together. Math, well understood. We know how to do it. It's the formulation of it that's going to be the issue. A lot of this might be useful to draw this shape on your homework so that way you can sketch on it. That might be useful. Please go ahead and do that. If I see a bunch of random shapes in your homework, I'm not going to think bad of you. I'm going to think good of you because you went forth, did the effort to make sure you understood it. Square roots. Ugh, why is that in geometry? Well, let's talk. If a number is a product of two identical factors, then either factor is called a square root. We know how to square something. We know what something is squared. So by definition, a square root would be the parts involved. Right? 3 times 3 is 9. Or we could say 3 squared is 9. There is my square, that 2 up there. That's where the square root connects to, that's where it gets its name, essentially, right? And we talked about, for example, squares. We started to catch a trend here, right? Squares, the area of a square is given by a number times itself. A square root relates to that square, which literally defines a square. What is the square root of, for example, 64? Well, a square root defines itself as something times itself equals, right? So in order to find the square root of 64, I need to know what squared equals 64. Or what times what equals 64. There's a square root on your calculator, but the idea would be stop and think about this stuff. Well, 8 times 8 is 64, so square root of 64 is 8. 12 times 12 is 144. The square root of 144 is 12. Or just use the square root button in your calculator. That works too. First 15 perfect squares. There's an argument to be made that's helpful to know the first 15 perfect squares. Meaning, what something times itself equals. Is the usefulness of this? There might be. I probably know all these off the top of my head, but that's more so because of running into this in math more so than running this in the real world. But then again, I don't know what you're going to do for a living. If knowing the first 15 perfect squares off the top of your head is something that's very useful to you, congratulations. Approximate square roots. If a number is not a perfect square, we can find its approximate square root. Square roots technically go on for a stupid amount of time. Some of them go on forever, actually. So, excuse me. It is useful sometimes to find approximate square roots or rounded values. Again, I don't know if this is something you're going to do in your day-to-day life. It's good to know what a square root is. It's very important to know what a square root is. Having the square root of 11 memorized, I don't know. I mean, that's something smart kids on like movies do to show they're really intelligent, right? Like the bad guy smart kid, you know? Oh, do you know the square root of 14.7? Oh, I do. I don't know. All right. That was square roots. Fun divergent, fun tangent. We all had a great time, right? We laughed, we cried. Let's move on to the Pythagorean theorem. I know you've heard the Pythagorean theorem before. That is one of those like phrases in math that's ubiquitous, right? Everyone's heard of it. Some of us know it, some of us don't. But with the Pythagorean theorem, named after some ancient dead Greek guy named Pythagoras, obviously, it states that the square of the hypotenuse of a right triangle equals the sum of the square of its two legs. Funny Simpsons joke about this too, if you watch The Simpsons. But oh God, what are we talking about here? Now we're throwing lots of different phrases at us, right? The Pythagorean theorem, those are big words. Hypotenuse, that's a big word. Hey, right triangle. I know right triangle. I know what equals means. I know what sum means. I know what squares means. Hey, I know what legs are. I have two legs. This has two legs. Hey, maybe we're getting someplace, right? The square, oh, there's no square there. So one thing I really don't know is Pythagorean theorem and hypotenuse. The Pythagorean theorem is just the name. So hypotenuse is the thing I got to wonder about, right? The hypotenuse is equal to the square of the hypotenuse is equal to the sum of the squares of the two legs. Cool. The hypotenuse of a right triangle is its longest side. Every right triangle, by definition, is going to have one side that's the longest. Right? This is not an equilateral triangle. All sides are equal. This is not an isosceles triangle with two sides of equal size. This is hypotenuse. This is a right triangle. All sides are different, but there's a 90-degree angle in it someplace. If you know the hypotenuse, you by definition can figure out the size of the legs. Or if you know the legs, you by definition can figure out the hypotenuse. The classic 3, 4, 5 triangle works out. 3 squared is 9, 4 squared is 16, 5, and then 9 plus 16 is 25. Square root of that is 5, giving us a right triangle. Not all right triangles follow 3, 4, 5, but this one does. And again, if you know how to use squares and square roots, this math is not difficult, right? Give me an equation. This equation suck. Essentially, what that equation would look like would be, if you, let's say I asked you for the hypotenuse, I would say x squared equals leg squared plus leg squared. And then you would have to solve for it. X squared equals 25, x equals 5. Right? That would be the steps you would take to solve this. Again, it's useful to write your equation out. The hypotenuse, for example, was the unknown and the legs were given. Find the hypotenuse of a right triangle with legs of 14 yards and 8 yards, right? Exactly what we said. This would be your hypotenuse, we'll say x is equal to 14 squared plus 8 squared, because the square of the legs. So then you get this stuff down. That would be, what's that, 196, because I memorized my perfect squares. Go me. 64, 260. So x squared equals 260. And now I just need to know what a square root is. A square root is the opposite of a square. So if I take this, essentially what you do is you take the square root of both sides. And the square root of any square is the number itself because it cancels it. The same thing to both sides. I would kind of wish the book would have gone into this a bit more. And then we go grab my red marker. Kabook, bow, bang, boom, boom. Those two blow each other up, leaving you with just an x. X equals a square root of 260, which I'm sorry I don't have memorized. Punch into my calculator, and you get 16.12. This says, I'm sure, there's a stupid amount of decimal points to it. Just give me a couple. I'm happy with that. Go to the hundreds or the thousands or something like that. It's fine. This square root conversation of building the equation is the important aspects of this conversation to have. Make sure that you know how to build this. Leave your variables as letters. You don't need to type out hypotenuse. You can just call it an x. That's fine. You don't need to type out leg if you don't want to. Very commonly, you will see, give me a spotlight. Very commonly, you will see these referred to as A, B, and C, where C tends to be the hypotenuse. And then there you go. You have variables say that A and B are interchangeable, essentially. But B base tends to be how you see it. It doesn't really matter if you have if you're really jiving on typing out the word hypotenuse in your homework, you go ahead and do that. Find lengths of legs, same basic concept, right? I know from the equation that 15 squared equals 11 squared plus leg, let's call that leg x squared. It's so hard to do it with a mouse. There we go. Solve for x. We know how to do this stuff, right? They go about math that we haven't covered too much, but you can break this math down easily. You know that these numbers, squares, was your order of operations. There's no parentheses shown here, so exponents come next. 15 squared is 225, because I'm so good at my perfect squares. 11 squared is 121 plus x squared. Cool. Subtract it over, get 104 equals x squared. Square root both sides. X equals the square root of 104. Oh my God, what am I doing? X equals the square root of 104, which roughly equals this. Take your time. Just because the book has it organized in this fashion, if that's not something that's jiving with you, write it down in your own way. I want you to be able to do it. I don't necessarily care you do it in the Pearson's Education Incorporated 2017 copyright version. I want you to be able to do it correctly, right? Joe runs out of gas in Plainsville, Indiana. Indiana, okay town, at least not in Ohio, right? Okay, state, I should say. He walks north for 3 miles, and then he walks 2 miles east looking for gas. How far is Joe away from his starting point? Well, in this case, I would suggest you draw a picture. Lucky for us, they drew a picture. We notice when we draw this out, his 3-mile walk north and then his 2-mile walk east kind of looks like a triangle. meaning this red line here is how far he is away from his start. We have a triangle. We have the red line being the longest part of that triangle. The red line is the hypotenuse. The legs are going the equation. Easy peasy lemon squeezy. This is an easy equation to solve for. We can do this math. We have that ability. It's just setting it up that can be the difficult part. I suggest using A, B, and C. C for the hypotenuse, A, B for the legs, or if you want, X, Y, Z. I don't really care what variables you use. I would suggest type of hypotenuse unless you love the word. It is kind of a cool looking word, I guess. It's got a Y and a P and a U, right? Lots of different letters. You don't see a whole lot. Joe's trek landed him about 3.61 miles away from his start point. Notice the hypotenuse 3.61 is larger than either 3 or 2. The hypotenuse is, by definition, larger than either leg. That makes sense. He walked 5 miles, but he only ended up being 3.61 miles away from where he started. The distance covered here is longer than the hypotenuse, but each individual leg is shorter than the hypotenuse. Definitions of triangles. What's the shortest point between two? What's the shortest distance between 2 points? A straight line, right? Excuse me. 30, 60, 90 triangles. These are 3, 4, 5 triangles, I believe. Shortcut way of doing it. If you like shortcuts, cool. Could be useful if you run into this exact triangle. Okay. 45, 45, 90 triangles. Another one that's exists out there. Again, you kind of run into a situation wherein this shortcut's useful if you are doing something that involves these common triangles. But the math, the underlying math, has not changed for the conversation. That's the key thing I want to bring up here. Cool. Find the lengths of sides X and Y. This is, so the book is skipping SOHCAHTOA and having you look at these equations here to find this information out. Again, when we're doing a homework, if you know SOHCAHTOA and you can solve this using SOHCAHTOA, go right ahead. I don't think we cover SOHCAHTOA in this class. It's next class. But if you know SOHCAHTOA, you can use SOHCAHTOA to sine, cosine, tangent. Sorry, if you know sine, cosine, tangent, those quantities, you can use that to solve this. If you don't know sine, cosine, tangent, notice that there's 45 degrees in this equation, and we just got done talking about a 45, 45, 90 triangle, wherein this equation down here gives you the information you need. Go back in the book, go back to the slideshow, shoot me a comment or an email. Hey, I'm lost. I can help you point in these directions. I prefer if you didn't use an automatic triangle calculator that you found off of Google. I want you to do the math. But yeah. Circles. We're circling in at the end of the lecture. That's a good one. Yeah. Circles. What is a circle? Well, you know what a circle is. A circle is a figure in which all points are at an equal distance from a given point. Definition, right? A circle looks like a circle. The center of the circle is the center of the circle. A line from the center of the circle to an outside edge, any outside edge, we call a radius. And a line crossing the inside of the circle at any angle is a diameter. Noteworthy here, that's a radius. That's a diameter. The angle doesn't matter for any of the diameter. I have to blow my nose soon, geez. And of course, a radius is half a diameter. A diameter is 2 radii. We don't talk perimeter when we talk circles. We instead use the word circumference. They're the same thing, but circles have their own special words because they're special that way. And they are special. The distance around a circle is called circumference, which is given in terms of pi. Pi, denoted by the symbol pi, is the number that we get when we divide the circumference of a circle by its diameter. If the diameter is 1, the circumference is 3.14. The diameter is 2, circumference is larger. There's some really, really cool animations as to how we find the number pi on YouTube. If you get the opportunity, I do suggest go watch a bit about how we determine pi. Numberphile, I think, has a video on it that's very interesting. And also, pi is one of those numbers that goes on forever without repeating, which is, again, cool stuff. But 3.14, 3.14, 15928 or whatever, it's all the same. 3.14 works just fine. Yep, so circumference is related to pi and diameter, as we talked about before. So you can find the circumference of a circle whose diameter is 5 by math. I'm going to suggest when you do these calculations, if your calculator has a pi button, use the pi button. It's going to be more accurate. Because the pi button has within it a bunch of digits that could be important for the answer. If you don't have access to a pi button, you can use 3.14, but by definition, your answer will be less accurate because there's 10,000 digits. There's hundreds of thousands of digits in pi. You can actually find your name in pi, probably. I think as Google find your name in pi and then type your name and you find out what digits spell out your name according to A equals 1, B equals 2, C equals 3. And that's kind of cool. I found my first name and my last name, but I did not find my complete name in pi. So some people have their entire name in the digits of pi. It's kind of cool, right? Area, pi r squared. You've probably heard that equation before. Again, right? Excuse me. I run into this issue with these examples where the math is easily understood. We know order of operations. We know how to square things or how to multiply things. It's just putting a new coat of paint on it, right? Instead of these being random numbers, they're now areas, pies, and radiuses. That being said, the math is something we know how to do. The math is something we have well practiced. We're good to go. There's no need at this point to be doing long form math. You do not need to put this into a vertical equation to calculate anymore. You can just use your calculator. That's fine. All I need to do is some basic understanding of steps. Maybe on your homework, you don't need to show this part right here. You can just set up your equation, fill in your equation with numbers, give me your answer. That's acceptable. If you got the correct answer and your equation set up correctly, I'm going to assume you did the middle parts right too. Yeah, this example here, find areas of unusual regions. We can look at this and figure out, okay, looks like this area is a square plus a half a circle. So I can figure out the size, the area of the rectangle, 18 and 10, well, that's 180, right? 18 times 10. And then I can figure out the area of this circle, because if I figure out the area from pi r squared, I can then think, well, half of the area of this what the circle would be is the area of half the circle, right? They do something interesting where, so they do it straight up. Sometimes textbooks like to fudge this stuff and use diameters since they give you a diameter, but a diameter is half a radius, so you know the radius is 5 by looking at this. Again, I'll say it. I've been saying it a few times in this class. I'm going to say it for the remaining chapters. It's hard for me to gauge how deep I need to go into this stuff because it is math we've already known. If you can set up the equation, you've done the hard part. And set up the equation will be difficult. I completely understand and I empathize with that. But take your time, write it out in long form. You'll get there, because once you write down once you have this skeleton of an equation set, it is easy to say, okay, where's my length? Well, there's my length, right? Where's my width? There's my width. Pi's known. Where's my radius? There's my radius. That stuff's all easy enough to find visually. The tricky part is this. And then once you know it and you filled everything in, order of operations. Don't screw up your order of operations. Do your square. Do your square first. Then do your multiplication. Then do your division. Then add them together. Take your time, follow order operations, you'll do just fine. Volume. More of the same. Volume is the measure of space inside a three-dimensional geometric figure. It's area, but we add a dimension, height, usually. So the area of this, if it was 2D, would be length times width. The height is same conversation, just add to the multiplication. Volume show up in cubes. So make sure to add 3, because that's how many dimensions we're talking about here, right? 3 different variables, a 3 above the unit. If there's 4 variables, you do a 4 above the unit. 5 variables, you do a 5 above the unit, etc., etc., etc. But the multiplication's easy enough. I don't need to belabor this too much, I imagine. Cylinders have their own certain equations. If you don't know the equation, just look it up. I mean, pi r squared h is the volume of a cylinder, but we're not in memorized geometry equations class, right? We're in math class. Feel free again, just to look stuff up if you don't know it. If you want, go to the slideshow, pause YouTube video, just Google volume of cylinder. It all works the same. I just want to make sure you're putting the equation, you're setting up the equation correctly, and you're solving the equation correctly. That's what I care about. The volume of a sphere, 4/3 pi r cubed, right? Yeah, exact same conversation. I mean, again, stop me at some point if you need to ask questions, or when I finish the recording, ask a question. But if you can write out the equation and you can figure out the variables involved, the math is something been doing all year, right? Find the volume of a sphere whose radius is 24 feet. Okay, so here is my equation. Volume is what I'm solving for. I only have one unknown. That's my radius. And my radius is 24 feet. So I just need to plug everything in. 4 times pi, which is a button on my calculator, times 24 cubed. The important part here is that cube relates directly to that radius. These two are connected. That's why we put them in parentheses like that. That's why that cube stays in that parenthesis. Exponents happen before multiplication, so we need to cube the radius before we start multiplying stuff. That's an important step. Talked about this a bit in fractions, but oops, sorry, let me draw a 3 there. There we go. This is the same thing as this. All right. If you want to put your 4/3 out front, fine. If you want to multiply by 4, divide by 3, like they do here, fine. Either way works. And we end up with a pretty big ball, right? 24-foot radius. That's a big ball. Volume of cone. I keep stressing it here. I'm not here to have you memorize equations. I'm here to have you do the equations correctly. Volume of a cone is pi r squared h divided by 3. Again, you can kind of if you picture what's going on here, you can see why it's divided by 3. Stack up your cones, opposite ends to get a complete shape, right? But I don't know. I mean, this is one of those issues where it's difficult to teach math over the internet because I can't look at you and see if you're confused, right? I'm going to go based on the assumption that we've been doing well with these sort of equations in math class so far, so you're going to be able to do well with these sort of equations in math class going forward. I make that assumption. Of course, email me, write down comments, Google it, ask your friends if you need the help, whatever you need to do to get there, because this stuff takes practice. The more you practice, the better you get at it, the better you get, the less you need to worry about it, right? Find over a period based on size divided by 3. Again, we can picture a pyramid, picture 3 of them together to get a complete shape sort of conversation here, right? Yeah, punching in numbers, right? I'm leaving on these slides a little bit, so when you go through this stuff in the YouTube video, if you want to pause and take notes, gather up what's going on here, that's cool. But it's plug in the numbers, solve the equation. The base here is given by length times width, right? So technically, I guess you could say LWH over 3 if you want. Same thing. The book is just stepping the problem ahead a beat or 2. Similar geometric figures. 2 triangles of the same shape but not necessarily the same size are called similar triangles. It's almost like they're similar or something, right? These are all the same shape, but the different sizes. So the sides, the legs, the hypotenuses, what have you, are different. Hypotenuse is only a term for right triangles, by the way. Yes, I believe that's correct. Scalene triangles, I do not believe have hypotenuses, although they do tend to have a longest side. Actually, I don't know. I have to look that up. Correct me if I'm wrong in the comments. I believe hypotenuse is exclusive to right triangle. Corresponding angles of similar triangles are equal because it's the same shape, just they are ratioed down, right? And corresponding sides, again, follow the ratio because the triangle follows the ratio. Can be useful. Again, we talked about ratios 2 chapters ago, and then this is the equivalent fractions conversation, right? 12 over 8 is 3 over 2, which is 9 over 6. We've done this math. I'm just putting a picture with it. 2 triangles are similar. Find the length of side n. Well, notice here the hypotenuses are 16 and 12, and the 10 and the n are on the same side relative to the hypotenuse. This would be adjacent if you know your SOHCAHTOA. So we land on this equation, which is something we've done plenty of. We know how to solve these things. This is cross multiply. We can do this. So if you can draw this equation, all this becomes irrelevant, right? Because that is the actual math going on. They have corresponding sides, therefore they are proportional to each other. They fit into the ratio. Yay! Perimeters of similar triangles and any similar figures have the same ratio as the corresponding sides. So if you know the sides, you know the perimeters, blah, 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 blah. Yeah. You shrink down objects are the same, they shrink down accordingly, right? This is what do you need to divide these out by? You get the same proportionality. Same ratios. Yeah, I don't see any questions. Feel free to do it in the comments, shoot me an email, message me on Moodle or Canvas, whatever we're using this week. Corresponding parts of other figures. Is this seeming old yet? Do I need to keep beating this dead horse? When you scale something down, everything scales accordingly. If it didn't scale accordingly, you have a different shape by definition. Easy enough stuff. We've done these conversations so much. It's just ratios, right? This is just ratios, but I put pretty pictures next to it. If you could do ratios just fine, you can do this stuff. Cross multiplication, what have you. Applied problems involving geometry. I believe this is the last chapter. And this is, I tell you a sentence before I show you the picture. Jessica's making cone-shaped candles. Good for Jessica. The mold for the candle is 4 inches in diameter and 7 inches high. How many cubic inches of wax does Jessica need to buy if she needs to make 50 candles? Not going on here, right? Well, not too much. Just pull out keywords here. 4-inch diameter, 7-inch high cone. Cool. Do I have an equation for cones? I do. If I know how much wax is needed to make 1 cone, can I figure out how much wax is needed to make 50 cones? Yes, I can. Once we break down this paragraph, we find that it is, in fact, not a difficult question. Pearson pushes this blueprint. They probably can sell you this if you want. But all I need to do is I need to look up the equation for the volume of a cone, pi r squared h divided by 3. I need to figure out how big that is. Well, remember correctly, my diameter was 4 inches. So if my diameter is 4 inches, what's my radius? Well, diameter is, radius is half a diameter. So that's 4 divided by 2, which means my radius is 2 inches. This r here is 2. So I land on pi times 2. The square stays with the 2. And then my height, I was told, was 7. Divided by 3. Follow my order of operations. Easy to solve, right? Do my square first, then multiply my top, and then divide my bottom. Landing on, takes each candle is about 29.3 cubic inches of wax. Multiply that by 50 to find the amount of wax I need. A little over 1,400 cubic inches. Not difficult math. Once I stop and think about what I'm looking at, pull out the information that's necessary, gather the facts, as Pearson's Education, Unlimited Corporate, All Rights Reserved 2017 says, pull out the information that's necessary, write down my equation, solve my variables. The math is easy to understand. A wallpaper hanger can wallpaper 100 square feet in 15 minutes. She would be papering 4 walls in a bedroom that measure 8 by 10, 8 by 12, 8 by 9, 8 by 10. How long will it take her? Ooh, that sounds like a lot, right? But think, what is wallpapering ability? Well, that's what, perimeter, right? So she can wallpaper 100 square feet. Then she needs to wallpaper, actually, no, it'd be area. Sorry, we're doing area conversation here, right? Because it's multiplication. Hey, I caught myself, right? She's going to wallpaper these walls. I was thinking these are rooms. That's why I was making my mistake. She wallpapered these walls in this very, I guess it's not a weird, it's a rectangle room. How long will it take her? Well, if I figure out the size of each wall, I can add them all up, divide by what I need. Area is length times width. An 8 by 10 room is 8 by 10 wall is 80 square feet. An 8 by 12 wall is 96 square feet. An 8 by 9 wall is 72 square feet. An 8 by 10 wall again is 80 square feet. Meaning this bedroom has 328 square feet of room in it. She can do 100. What could she do? She can do 100 square feet in 15 minutes. So how long is it going to take her to do 328 square feet? Well, now we can do that basic unit conversion we talked about last time. Takes her 15 minutes to do 100 square feet. It's going to take her. She's going to have She's going to have 4,920 minutes of work per foot, or 49. My God, words suck today. 49.2 minutes to do the job, because she can wallpaper 100 square foot in 15 minutes. Honestly, what I think the hardest part of this entire question is this little unit conversion at the end, because the book has not done a good job. Sorry, Pearson's culprit lords. And I do not think the book's done a good job of doing these unit conversions. But if we write this stuff down, solve unit, top, unit, bottom, cancel, put in the information where it needs to go, we can get there, right? Because at the end of the day, this guy here is 100 feet per 15 minutes, or it's 15 minutes per 100 square feet. So when I write down my equation here, I choose the one that cancels out what I need. I need feet at the bottom. That's the equation. I need, right? We talked about that last chapter, I want to say. Maybe chapter before that. There you go. That is chapter 7. A lot of beat a dead horse here. We've done this math already. We just need to look at it through a different lens, different context. It's all just been addition and multiplication, a little bit of division. Make sure to leave any comments in the YouTube video down below if you have any questions. You want me to go more in depth into something. Just take your time on your homework. Don't just try to cram it all in last minute, right? You can spend a half hour every day working on a little bit, write it out. Let me know if you run out of paper for some reason to go plant a tree and start growing you some. Yeah, you can do it. Definitely doable. Definitely something that can be solved. So that has been the conversation. I'll stop the recording, and then we can go on to any questions if you need them. Thanks for watching.